leg vascular resistance. So here we have leg vascular resistance relative to the work of breathing, leg blood flow relative to the work of breathing, leg VO2 relative to the work of breathing, and leg oxygen uptake relative to whole body oxygen uptake. So what I'm showing you here is that all of these values are expressed as the vascular resistance, blood flow, and leg VO2 are expressed as a percentage of control. So basically the normal breathing condition where the work of breathing was normal. So you can see here, this at 100% is the condition where the work of breathing was normal, and then they unloaded the work of breathing experimentally, and then they loaded the work of breathing experimentally. And here they're looking at the leg vascular resistance effect relative, again, to the unloaded breathing condition. And so the take-home messages here is that as the work of breathing increased, leg vascular resistance increased. So again, maybe there is a sympathetically mediated vasoconstriction that can originate from the respiratory muscles. You load the respiratory muscles, leg vascular resistance goes up. Presumably that's through the greater sympathetic activation acting on the vasculature of the limb locomotor muscles. You unload the respiratory muscles, it declines. If you increase resistance or decrease conductance, what happens to blood flow? As you increase the work of breathing, and you increase leg vascular resistance, or you decrease leg vascular conductance, leg blood flow goes down. You're basically imposing a limit to blood flow to those peripheral muscles. So oxygen delivery is equal to limb blood flow times by arterial oxygen content. So if the changes in the work of breathing had no effect on oxygen saturation levels but decreased limb blood flow, what would happen to limb oxygen delivery? It goes down, right? Because you're decreasing limb blood flow at a constant oxygen content. So net oxygen delivery to the limbs go down. If you look at the rate of oxygen consumption generated by the legs, resistance goes up, blood flow goes down, leg VO2 goes down. So you're delivering less oxygen, it's using less oxygen. And it makes sense then that the leg VO2 relative to the whole body VO2 deteriorates as well. So now the leg oxygen uptake is actually contributing progressively less to the whole body VO2. Imagine if you looked at the VO2 of the respiratory muscles, you'd presume that it would be increasing, such that whole body VO2 is, say, staying consistent, but the relative contribution of the leg VO2 to the respiratory muscle VO2 are now shifting. Blood is moving away from the limbs towards the respiratory muscles. So you achieve the same whole body VO2, but the contributions to that whole body oxygen uptake are shifting in proportion to where the blood is being redistributed. So again, this is another kind of step to add on to that hypothesis that loading the respiratory muscles, or even that the changes in the work of breathing going from 100 to below, unloading the system are, again, physiologically, they're the most important, right? Because that's saying that the work of breathing that's normally incurred is resulting in higher vascular resistance, lower blood flow, lower leg VO2, and a lower percentage of the total VO2 than if the work of breathing was able to be reduced in these athletes. So the normal week of work of breathing incurred is contributing to some increase in limb vascular resistance, decrease in leg blood flow, oxygen delivery, and oxygen consumption. So, several years later, Lee Romer again, with Jerry Dempsey, did a study in 8 male endurance trained cyclists on a cycloergometer, at a very high intensity to exhaustion. Same design. On a separate occasion, subjects exercised for the same duration and at the same power output as control, but the work of breathing was decreased by about 50% compared to the control condition, again using a mechanical ventilator. They looked at quadriceps muscle fatigue. So in the previous ones, they just looked at blood flow. Now they're looking at the level of fatigue development using that femoral nerve twitch procedure. And so what would you expect to happen based on what you've seen there? You take these athletes, you exercise them at a high intensity, at a constant duration. You unload the respiratory muscles. Would you expect that the magnitude of quadriceps twitch force loss in the unloaded condition would be greater than control or less than control? In other words, would the muscle be more fatigued or less fatigued after a fixed period of time of exercise at a given exercise intensity with less work of breathing compared to the normal work of breathing? Less. So again, the bar coming down in terms of the twitch force loss would be closer towards 0, right? So again, experimental design. To bring it all back to, I think, lecture 1 or 2, this concept of what the muscle is able to do. This is, remember, this dotted line represents the rate of development of muscle fatigue development. So the idea here, the idea is that the work of breathing will decrease the rate of development of fatigue relative to control performed at the same time, which means that we should have less muscle fatigue development or a lesser percentage loss of muscle force in relation to a magnetic maximum twitch of the nerve. And what happens? So, when you unload the respiratory system using a mechanical ventilator compared to control, you can attenuate the rate of development of peripheral muscle fatigue. So the amount of force production loss when you unload the respiratory muscles by 55% does not eliminate fatigue development, but it certainly slows it down. So the implications here are that these athletes, if allowed to exercise beyond 13.2 minutes, would have just continued to exercise until the capacity of the muscle intersected with the demands imposed on the muscle. And so they would have had a longer exercise endurance time when you unloaded the respiratory system. So, the peripheral fatigue of the locomotor muscles resulting from high intensity sustained exercise is due, in part, to the high levels of respiratory muscle work that we've seen can compromise limb blood flow by activating or increase limb vascular resistance. And so again, this is the concept of that respiratory muscle steal phenomenon, shifting blood away from the peripheral muscles, presumably towards the respiratory to support their very high work and oxygen demands. So the last two experiments, these are brand new. This is a colleague from UBC. If anybody is really interested in really nice kind of integrated athlete exercise physiology, there's a guy called Bill Scheel. He works at UBC. He's a full professor. And there's a young man called Paolo Dominelli who's now at the Mayo Clinic working with the guy Bruce Johnson. And they do some really, really nice stuff where they built a mechanical ventilator and they do some near-infrared spectroscopy measures and diaphragm EMG and anyways, they do some really, really cool integrated physiology stuff. So if you want to not be in Montreal and you want to do graduate work and you want to be hanging out in the mountains and going down and seeing seals in the ocean and all this type of stuff, BC is a pretty cool place to go, and they're a pretty interesting lab that do a lot of this type of stuff. So this is some work that Paolo did with Bill, and I believe they also did some work with Katayama in Korea or Japan, but pretty cool physiology that they did here. So here's a study building on that work from Craig Harms and Jerry Dempsey. And again, Bill Scheel trained with Jerry Dempsey, so you see that it's all, a couple of degrees of separation between the master. But 8 healthy adults, 25 years, VO2, again, about 55 mils per kg. Constant load cycle exercise at 90% to peak incremental power output. You see a similar theme here. Now what they did is the work of breathing was assessed with esophageal balloon catheters. So again, a balloon they put in through the nose down to the esophagus so they can measure respiratory pressure swings in relation to tidal volume expansion. And the work of breathing was increased using inspiratory and expiratory resistors. So they really put a load on the respiratory system here. They just didn't put it on inspiration. They basically put a resistor. They made them breathe through filter paper both on in and out. So every breath in was harder and every breath out was harder. So they basically activated both the inspiratory muscles and expiratory muscles to really work very hard. So they really jacked up the work of breathing. They also decreased the work of breathing using this mechanical ventilator that they built themselves, which is pretty crazy, or they had the control condition. They assessed blood flow using near-infrared spectroscopy. So if you guys seen this, it's basically like a surface optode electrode that can measure kind of like reflect the myoglobin levels, desaturation levels of myoglobin and hemoglobin. It can get a measurement of basically like microvascular tissue oxygenation. I'm not an expert in it, clearly, but the idea is that it can measure, it gives you an estimate of muscle oxygenation levels, how much their level of desaturation kind of subcutaneously. And then if you pair these measurements with injection of this dye, so this what they call ICG, you can actually measure from the bolus injection into a vein and its appearance at the muscle. You can actually get an index of blood flow. So you can measure muscle oxygenation and you can get an index of blood flow based on when when the dye is injected, and then basically its appearance in the optode that shows up during exercise. So you can get this blood flow index. And they place these near-infrared spectroscopy optodes over the quadricep, both the vastus lateralis and medialis, and the sternocleidomastoid. So basically an accessory muscle of inspiration, which would have to be activated when the respiratory system is loaded and deactivated when it's unloaded. Right? The sternocleidomastoid would really help to try to pull the rib cage open and up when the other inspiratory muscles are burdened heavily by these resistors. So this is just, they always present these data. This is just an experiment. This is from an individual subject. So this is the balloon that's put through the nose and a balloon that sits in the esophagus that measures intrapulmonary pressure swings. And so here you can see this is inspiration where the pressure goes negative, expiration, inspiration, expiration, in, out, in, out, in, out. So this is when the mechanical ventilator is on. This is when there's no intervention, and this is when there's the resistances. So you can see that in the control condition, they pull pretty big negative pressures and pretty big positive pressures. So this is like all of the inspiratory muscles acting, and this is all of the expiratory muscles acting. So this is they're working pretty hard to move swings of air and move air into and out of the lungs. You can see when the ventilator is on, the ventilator does most of the work. And you can see here that their ventilation's 214 liters a minute and 221 liters a minute. Really quite comparable. So the work of breathing is dramatically reduced at similar levels of ventilation. When you add the resistance, you can see a similar level of ventilation. If anything, it's a little bit less. But look they're pulling pretty big negative pressures and pushing pretty big positive pressures. So they're getting these pretty dramatic respiratory pressure swings. And you can see down here the sternocleidomastoid EMG. So on inspiration, a few bursts, inspiration, a few bursts. During inspiration in the control condition, a definitive burst. And you can see here on the resistance, they're really activating those sternocleidomastoid muscles to really try to assist ventilation. So they're getting some indication of inspiratory muscle activity and inspiratory muscle blood flow, as well as quadriceps muscle blood flow and activity. When they average these data across their 10 or 12 or 11 subjects, 10, is that what I say, 10? What they see is that as relative to the control condition, again, which is 100% of the work of breathing, so this is with no intervention, so that middle condition, the middle panel that I showed you on the previous slide, the proportional assisted ventilator decreased the work of breathing by about 50%, and the resistive loader increased it by about 30% relative to control. So the experimental intervention worked. They loaded and unloaded the work of breathing. If you look at the EMG activity of the sternocleidomastoid on the resistance and on the mechanical ventilator, the vastus lateralis and medialis under the two experimental conditions, you can see that the limb muscle didn't change its level of activation. Okay, so you didn't necessarily have vastus lateralis or medialis mediated recruitment of motor units. But what you did see is that you did have, in the resistive condition, the sternocleidomastoid muscles were activated and deactivated in the unloaded condition. So, higher activation of the accessory muscles, deactivation of the accessory muscles of inspiration. So the key to this observation is basically now is that if you look at sternocleidomastoid blood flow, vastus lateralis blood flow, and vastus medialis blood flow. Again, you see a similar plot. Here's the blood flow under control conditions as the horizontal line, and this is the work of breathing as the vertical line in each graph. You can see is that when the work of breathing was decreased, sternocleidomastoid muscle blood flow was lower than control, and when the work of breathing was increased, it was higher than control with a variable but linear correlation. And you saw the opposite. When they decreased the work of breathing, they got a higher blood flow index at the same level of motor unit activation, which makes sense, right? You don't necessarily have to activate the muscle to support the same level of metabolic demand or the same power output if you're sending more blood. So you can go back to the oxygen conformer and the net drive hypotheses and those oxygen in the time trial studies, and you should be able to interpret these data in the context of those results because they all fit. I'm going to leave that with you. It'll be a good kind of study note for the exam. Okay? So the idea is that when you unload the work of breathing, the vastus lateralis and medialis get more blood, and when you increase the work of breathing, it gets less blood compared to the control condition. So again, taking it one step further, now they're actually showing that you're getting more blood flow in the unloaded condition to the sternocleidomastoid and less blood flow to the periphery. So now this is the first study that's actually done simultaneous measures of blood flow to both respiratory muscles, to both the respiratory and the peripheral muscle. Okay? So when the work of breathing decreased, respiratory muscle blood flow decreased and quadriceps blood flow increased. When the work of breathing increased, respiratory muscle blood flow increased while quadriceps blood flow decreased. So these findings support the respiratory muscle steal hypothesis, which that is when the respiratory demand for blood flow is reduced, additional blood can be directed towards the active muscles, meaning that again, this is key, the high respiratory muscle work normally incurred during heavy exercise attenuates blood flow to the locomotor muscles. You compromise blood flow, you compromise oxygen delivery. We know that oxygen delivery is directly related to intracellular PO2. So you decrease oxygen delivery, you decrease intracellular PO2, you would need metabolic adjustments that would increase the rate of development of peripheral muscle fatigue, like I showed you on the rower studies before. 13.2 minutes at 294 watts, take them off when you either prevent or have exercise-induced hypoxemia, or you have normal or unloaded work of breathing. The net effect is that the magnitude of quadriceps twitch force loss is less when you can support higher oxygen delivery. So to bring this all around, Paulo and them very recently published a paper where the goal was to assess muscle sympathetic nerve activity when the work of breathing was experimentally lowered during dynamic exercise. So that's that last bit of the equation that we need, right? We need to know that if we unload the work of breathing, do we get corresponding changes in muscle sympathetic nerve activity to show that the work of breathing can signal a change in sympathetic activation that would have effect on these, that could explain these effects that we see on blood flow and fatigue development. So we needed that kind of additional mechanistic insight to try to really bring this hypothesis together. So this was a study of 12 healthy adults, again, not particularly fit, performed semi-recumbent cycling trials at 40, 60, and 80% of peak incremental power output. I'm only going to show you the data at 60 and 80%. Exercise trials consisted of spontaneous breathing, reduced work of breathing using that ventilator again, followed by further spontaneous breathing, where the major points of comparison here were the unloaded breathing, followed by the spontaneous post-ventilator breathing. And muscle sympathetic nerve activity was actually recorded from the median nerve. So what Charlotte does in her lab, Charlotte actually records muscle sympathetic nerve activity from the peroneal nerve, which is in the lower limb, but you can't do whole body exercise while you do that. And like you can't do lower limb exercises, so then you just can't do it. It's like technically it would be impossible. So a major feat that these guys accomplished is actually measuring muscle sympathetic nerve activity during submaximal and near maximal exercise, but using the median nerve instead. So they were able to isolate and keep the arms still, measure sympathetic nerve activity of the upper body while they were exercising the lower body. Like, just from a technological standpoint, it's pretty impressive. to say this, they're the first ones that have done this, at least with heart-lung kind of muscle interaction. So what I'm showing you here then is that here I'm showing you muscle sympathetic nerve activity. This is the burst frequency, so the number of nerve bursts per minute, the minute ventilation, and the work of breathing. During the 60% trial and the 80% trial, this is exercise time, this is the spontaneous breathing, this is the period of time where the ventilator was on, and here's the period of time when the ventilator was withdrawn, but they basically recovered from that work of breathing. So what I want you to do is I just want you to focus on the PAV and the recovery conditions for the interpretation of these data, okay? So you can see here that at 60% peak power output, you can see that compared to the post-ventilator condition, muscle sympathetic nerve activity was attenuated when they decreased the work of breathing. So the work of breathing was decreased in the unloading condition compared to the normal breathing condition. Ventilation was actually quite similar between the unloaded and normal breathing condition, but when you unloaded the respiratory muscles with the mechanical ventilator, you got a relative decrease in muscle sympathetic nerve activity compared to when the ventilator was off. And you can see that this occurred at 60% peak power output and also occurred at 80% peak power output. So again, muscle sympathetic nerve activity was blunted relative to the ventilator off condition, minute ventilation was similar, and the work of breathing was reduced. So the idea here again is that decreasing the work of breathing, at least during moderate and heavy intensity exercise, when the ventilatory demands are on the order of, you're looking at 85 to 90 to about 120 and 130 liters a minute, can cause this reflex increase in sympathetic nerve activity that can compromise limb blood flow. So if you start combining the studies together, decreasing the work of breathing decreases the blood flow to the respiratory muscles and increases it to the peripheral muscles. When you unload the work of breathing, you would have less muscle sympathetic nerve activity, which means that you would have less vasoconstricting influence on those lower limb muscles, likely contributing or explaining why the blood flow was higher when you unloaded the respiratory muscles to both the blood flow to the vastus lateralis and medialis. So again, this brings this whole respiratory muscle steal hypothesis into light. Loaded muscles can activate the sympathetic nervous system. That sympathetic nervous system can exert its effects on the peripheral muscles, causing vasoconstriction. That vasoconstriction can compromise oxygen delivery. And compromised oxygen delivery to support a given power output or a given oxygen uptake requirement will result in an increased rate of development of fatigue, because it's going to result in an accumulation of inorganic phosphate. Phosphocreatine is going to be degraded to a greater extent. There's going to be intramuscular acidosis that occurs. Okay? Greater symptom burden. And so the conclusion from this study is that lowering the normally occurring work of breathing during moderate to heavy intensity exercise resulted in commensurate reductions in muscle sympathetic nerve activity. And these findings provide, to my knowledge, the first bit of experimental evidence of a sympathetically mediated vasoconstrictor effect on the locomotor muscle vasculature that originates in the respiratory muscles. So when respiratory muscle demand for blood flow is reduced during moderate to heavy intensity exercise, MSNA is reduced, meaning that the high respiratory muscle work normally incurred during moderate to heavy intensity exercise can attenuate blood flow to those muscles via sympathetic mediated vasoconstriction. And so ideally, you should be able to take all of this and fit it into the net drive and oxygen conformer hypotheses. Because really now the work of breathing has just become one other mechanism that can compromise intracellular PO2. Right? So I should be able to, that graph that I showed you, go from normal, I should be able to put, at this point you unload the work of breathing, at this point you load the work of breathing, at this point you unload the work of breathing, and then you cause hypoxia. At this point, you load the work of breathing and then you give hyperoxia. You should be able to take and track and change any one of those parameters because you know what the effect is of loading and unloading. The effect of loading and unloading is on muscle sympathetic nerve activity. The effect of loading and unloading is on vascular conductance. The effect of loading and unloading is on sympathetic nerve activity, vascular conductance, and therefore blood flow. The effect of blood flow on intracellular PO2. The effect of intracellular PO2 on the other metabolic processes. So at this stage, it doesn't matter what manipulation I give you. You should ultimately be, how is this going to affect oxygen state of the muscle? And then everything from that should be pretty easy to answer. Right? So, there's our Bitmojis. I think mine looks more like me than hers, but I'm just competitive like that. So, anyways, good luck on your exams. You're going to get an email. The lab number 5, so a pretty horrific event. My external hard drive, I told you I was out and back, like I don't know how many hours I spent, and so getting back and forth and getting this thing. I got it, clearly I posted the data, but then we've been informed that the deadline is actually carries into the exam period, and it's kind of it's touchy-feely with the assessment policy of McGill. So what we've decided to do in an email will come out